All right, welcome back. This is lecture 11 and our very last lecture. We have a whole bunch of pre-frosh here with us today, so everyone should please be nice and smart. And the pre-frosh who are in the room, you guys should certainly feel free to ask questions if they arise, and also if you need to get to other pre-froshy things, you're welcome to depart whenever you need to. Today is about security. And this is a topic that applies mostly to things server side, whether you're actually using iOS hardware or some other mobile device, or are doing purely web-based server-side development. And really the objective today is not necessarily to put forth answers to a whole bunch of non-obvious security questions, but really to start get you guys thinking about what should you be thinking about when you design software that other people are actually going to use, particularly when some of those people are malicious or simply do things that you don't intend. And indeed, certainly being Harvard undergrads with lots of techie friends, if and when you do work on your next project or your next startup, rest assured that at least one of your friends late at night is going to try to shame you by finding some fatal flaw in your tool that you've developed online. And we see this all the time in CS50. And it takes just days for people to start poking holes in various popular CS50 projects. So the goal ultimately is to get you to start thinking defensively. So a fun thing to start with is this here tool, which you may have played with a year or so ago. And some of you may have seen these screenshots in the past. But just to get you cognizant about some of the data that's accessible for better or for worse these days, this tool was released just about a year ago when it became known that Apple's iTunes had not been encrypting geolocation data that it had been tracking. So this is disclosed if you read the 27-page terms of service document before you use an iPhone device or an iOS device. You will see in there that Apple reserves the right to track your location for a couple of reasons, and we'll come back to that. But what they were doing initially in iTunes is not encrypting that information with your Apple ID or anything like that. So the implication was if that anyone else had physical access to your laptop or your Mac desktop, whether it's friend, roommate, fiance, spouse, whatnot, that person could see everywhere you've been. And you can imagine some fun scenarios in which that's not necessarily a good thing. So I ran this on my own phone a while back. And I saw this picture arise. So this context, again, it's just a big XML file that iTunes stores on one's hard drive. And if you analyze the GPS coordinates in it, you can then plot it on a graph, on a map, which this here tool did. And you can see that around that time, or at least as long as I had that particular iPhone, spent a lot of time in the Northeast. I went to Texas, went to Pennsylvania, went to San Francisco, and thereabouts. But if you dive in deeper, you can see just how granular this data is. So this is zoomed in on the Boston area, and the very blue splotch is mostly over Boston and the Cambridge area, where I do spend a good amount of time. And then the dots elsewhere suggest little random trips I made to the suburbs and the like. But you can see other data if we zoom out a little bit. I did that year a lot of commuting back and forth to New York. And you can literally see me on Amtrak starting at top right, which is the big blue dot in Boston, going down there to New York, going down further to Stamford, Connecticut, and you can see the density of just either how long the Amtrak trains took or how many times I went back and forth on this route. And I also vacationed briefly on Cape Cod that year, which you can see there in the little hook of a map. So if we zoom out, this was kind of fun because I actually, when I looked at this data, had no recollection of actually being in Pennsylvania. And I was wondering why my phone had apparently been there in western Pennsylvania. And then I realized that I had, in fact, visited Carnegie Mellon that year. So that wasn't a huge surprise. And then you can look a little closer at some of the data in the West Coast and the like, and even see some of the flight paths that I took in making travels that year. So all kind of fun and interesting. And you might be able to use this tool still if you're able to decrypt the file that's still resident on your computer. But let's take a step back. Why does Apple need to know everywhere I have been in this fashion? And why is this all being logged in the first place? Yeah. Okay, so for ads, right, it's actually kind of a compelling story to be able to walk past Starbucks or something like that, and in theory, be able to get some push notification that says, hey, come into Starbucks now and we'll give you half price or something like that. So geolocation can actually be beneficial, certainly for the advertisers, and maybe for the consumer, if not too invasive.
Wi-Fi hotspot tags?
Wi-Fi hotspot tags, what do you mean by that?
Like adhere a location to certain Wi-Fi hotspots if your Wi-Fi has been turned on
Oh.
while you're traveling.
Okay. So be more concrete. What's the relationship between the GPS coordinates and Wi-Fi here?
So like if there's a Wi-Fi hotspot that doesn't already have a location associated with it,
Good.
you can associate the location with it.
Okay, exactly. So you might know that over the years, companies like Google have done a lot of war driving, which means driving around in a special car that actually listens for Wi-Fi hotspots so that you can actually plot out where various SSIDs are. By SSID on campus, I mean something like Harvard University, or if you're at home, maybe quote-unquote Linksys, or whatever the default names or customized names are for these access points. But Apple and Google and the like certainly don't know where my access point is. But if someone drives past my apartment, and that device has a GPS transponder in it, and therefore knows precisely what the latitude longitudinal coordinates are of the car or the person at that moment in time, and that person's phone also hears, in addition to talking to the GPS satellite, also hears my SSID from home, or Harvard University's SSID from home, now that person's phone, even if it's some random stranger on the street, can upload it to Apple and inform them, hey, next time you see quote-unquote Harvard University, it's at these GPS coordinates. So those of you who only have iPod touches or devices that don't have GPS transponders, you can still use things like Google Maps and hit location, and it can find you with pretty decent accuracy, at least within a bunch of meters, and that's typically because the device is checking what access points can I hear. I hear Harvard University, I hear Starbucks, I hear the Coop, and you can do sort of triangulation style geolocation without using actual GPS. So that's kind of a win overall, and it requires that no one has to drive around constantly looking for this, because you now have millions of us people doing this for these companies.
On a similar note, Apple puts hotspots of their own all over the place.
Okay.
It's good for them to know where people are on computers so they can figure out what has those demand.
Demand in what sense?
Demand for internet hotspots, where they should
Okay.
be.
Okay, good. So you can use it to actually infer what kind of density you should have in terms of Wi-Fi hotspots. And as you all probably know, this building, for instance, has no wireless connectivity. As an aside, it's apparently for historical reasons. There's a historical society that doesn't want us sullying the walls with antennas and whatnot. Ironic given the other hardware that's in here, but that's why, but they're working on it. So that could, too, be another reason as well. So with the cool thing, at least from a developer's perspective, is that you actually then have access to really interesting data. And you have the ability to geolocate users, to figure out where they are. You can do creepy things like finding your friends on Android devices and iOS devices now, all because we're kind of walking around with these things in our pocket. So this is only to say, now that you have all this more information available to you, for better or for worse, the onus becomes on you to actually keep this information, whether developer or person, safe or safer, and recognize what could be divulged. So more generally then, what are some obvious threats to security? So here's a list, some of whose protocols you might know, some of which you might not. In what sense do HTTP and MySQL, two of the more familiar, pose threats to security of person or application, would you say? What are the scenarios you have to worry about if you just know that some website or some app is using these tools? Yeah?
Cross-site scripting.
Okay, cross-site scripting, what's that?
It's injecting pieces of JavaScript, for example, in user input to a website.
Okay.
And then executed when it gets displayed on the page.
Okay, good. So cross-site scripting refers to this somehow kind of injection of JavaScript code into some website such that the user is tricked into executing it. And we'll see some examples actually today of that. So that relates, of course, to, I guess, to HTTP, but even higher level. That relates really to HTML and JavaScript and the like. Yeah? Good.
Or they could put some SQL code in there, query your database, either get information out or do horrible things to it.
Perfect. So there's SQL injection attacks, which we'll see also some example of, but in a nutshell, this refers to the ability of an adversary or even just some user to accidentally execute SQL queries on your database because you, the developer, have not actually scrubbed user inputs, which simply means making sure that there aren't dangerous characters like quotes and semicolons and things that could be mistaken for actual database queries. Yeah?
Also, the fact that MySQL is so centralized, allowing so somebody is able to hack into one password, they can get all the information instantaneously.
Yeah, so the centralization of most databases, MySQL among them, is actually kind of a serious thing. There's certainly convenience of having your user's database and their email addresses and their credit card numbers and passwords or hashes thereof, plus address information, purchasing history. I mean, it makes sense, and especially when we talk about database design, to have all of this data in the same database, maybe separate tables for design's sake, but in the same place. But that just means if one person gets into this database, then potentially all of your data might be compromised. And so one of the things we didn't talk about this semester, but things you can do with tools like MySQL is you can absolutely create separate user accounts, usernames and passwords that have different privileges. In fact, if you go back and poke around with phpMyAdmin and you log in as root on the appliance, for instance, with password Crimson, there's a privileges tab, and you can see there that you can create any number of usernames. And so quite common, especially if you want to be adhering to best security practices, you would have usernames for MySQL that, for instance, can only do selects, and another username that can only do inserts. So at least you're refining the scope of someone's capabilities so that if one of those accounts is compromised, at least you don't lose everything. And there's been some fascinating stories, right? Like Sony, for instance, is not very good, as best we can tell, at security, since like their PS3 and PS2 database keeps getting compromised, I think twice in 1 year. And you always hear these stories about people who are not even encrypting in things like one's password. How about things like credit card information? Can or should you encrypt those in a database? What kinds of thought? If you're now writing an app that needs to take payments and you're doing the processing yourselves, is this something you should encrypt, do you think? Why not?
You shouldn't really be storing.
What's that?
You shouldn't really be storing credit card information in the first place.
Okay, so shouldn't really be storing credit card information in the first place, but suppose my customers have demanded that they not type this in every month for a recurring service, so I want to do automatic bill pay.
Encrypt the hell out of it.
Okay, so let's go there. So I encrypt it. So, okay, I learned in past lives to encrypt, or at least to hash, one-way hash my passwords. So let's one-way hash the credit card numbers. Secure? So it's technically secure, right? But
You can't use it if you need to do transactions.
exactly. So if you just take a one-way hash, the name should kind of spoil the answer there, is that that's bad, right? Because you can never get the credit card number back. You only have the enciphered form.
Isn't that what the sort of the security number in the back is supposed to like use that as use that as like the key?
So it's actually a good idea. So you do have these secret numbers, these 3 or 4 digit numbers on the back or the front of an Amex card or a Visa or MasterCard, and that's meant to be more private than the number. So you could use those as keys. They're not terribly long, to be honest, so an adversary could probably figure out 3-digit codes pretty easily. But a compromise could be just store the credit card number in the clear, as is actually fairly common. But what should you not store, perhaps? You could at least not store the 3 or 4-digit code so that at least the user doesn't have to type in the entire sequence every time, but they do have to verify that code. And as to what you can do typically depends on the service agreements that you have with the credit card provider and what the fine print actually says. Or in theory, you could outsource this. I mean, that's actually a reasonable option to someone else such that it's their problem. That doesn't mean they're doing it correctly as well. But what if we did two-way? What if we did an actual encryption? So not a hash. So we had a secret key that we use on our site to encrypt credit card numbers and then decrypt them on demand.
Well, presumably, if they were able to get access to your database, they could also get access to your server and figure out what the key was.
Yeah, so exactly. So there's still this risk. We've maybe raised the bar a little bit to the bad guys, but if you're doing this in an automated web environment and you have a secret key, that key needs to be used to decrypt credit cards, which means it's either got to be in a kid and fig file, or a sysadmin has to at least type it once when the server boots so that it can remain resident in RAM so that you can actually decrypt it. So of course, if the bad guy has access to the machine and can not only get the database encrypted, those parts of it may be, if you can also get the key, well, you've not really accomplished all that much. But indeed, some servers do support this, whereby it's annoying, but sysadmins can in fact type the password once when the computer boots, and as long as that server is operational, the key is in memory, but at least it's not on disk, which means an adversary might compromise the system, might get a copy of the database, but he's not very easily going to find the password unless he starts doing the equivalent of something like GDB and poking around in memory, which is going to be much more complicated than most adversaries are generally capable of, certainly when these attacks are waged with script kiddie style with automated scripts. Other questions or comments? Okay. All right, so in short, again, no clear-cut answer here, but if you're not even thinking about it, that's bad, right? And someone's going to trip you up somewhere. And this is the fun or perhaps disconcerting thing about security. Like security, the good guys really have it fundamentally the worst, right? The bad guys have to find one and only one hole in your entire design in order to potentially compromise your data, steal your customers, or just wreak havoc on your intellectual property. But the good guys, meanwhile, to defend themselves have to do what in order to avoid that? You have to fill like all possible security holes. So this is kind of a losing proposition in the first place. And so one of the biggest motivations to just be paranoid is for that same reason. The bad guy only has to find one unlocked window in a building of hundreds of windows or hundreds of lines of code. It's up to you to actually lock all of those things. And it's hard until you get into this kind of habit. So for those unfamiliar, or for at least one person familiar, what's Telnet? It's still used in some places. Yeah.
It's a very primitive protocol to access computers over a network.
Good. So it's a primitive protocol for accessing a computer over the network using a command line interface. And we can simplify it as it's SSH, but without any encryption whatsoever. And so back in my day when we had FAS email accounts, and we used to connect to the Science Center computers to actually access email, it was actually all via Telnet. And so all of our FAS usernames and passwords for years were just transmitted over the clear. Now, one thing that mitigated that at the time was that there was no, well, and to this day, there's no Wi-Fi, right? So at least it's not all that easy to sniff the data wirelessly. Someone would have had to physically patch into network jacks that were broadcasting information. But this was the thing, too. Back in 95, 96, and a few years thereafter, instead of having these devices called switches on campus and in lots of places in the world, there were things called hubs. And as an aside, anyone know the difference between a network switch and a network hub? Yeah.
So switches channel the network dynamically, whereas hubs are just like static division of the network.
OK, good. And let me, what do you mean by static division?
Like every port gets the same amount of network, I guess.
OK, yeah, and let me tweak slightly. Whereas a switch, if a switch has like 5 Ethernet ports, 10 or 100, a switch can generally guarantee a specific amount of bandwidth, like 100 megabits per physical port, whereas a hub shares that bandwidth across all of them. But worse for security, whereas a switch, if it has 5 ports and computer A wants to talk to computer B, and A is here and B is here, the switch is smart enough that after 1 or 2 packets go through it to figure out A is here, B is here. So henceforth, when A sends B a message, it only goes through A's port and then out B's port. But a hub, by contrast, is literally a dumb and less expensive device. If A wants to talk to B, that packet goes from A and then down to B, C, D, and E, irrespective of whether or not they actually want that data. So back in the day, when I lived in Mather House, in theory, with the right tool, I could plug my laptop or desktop into a network jack on campus, and I could absolutely see all of the emails and the instant messages that my roommate one door over was sending because he was physically connected to the same hub. And I dare say this is not completely eliminated from the world, having this kind of hardware. And even with switches, there's the capability to at least see some of someone's data. And just since this is always fun, and this is one of those do as I say, not as I do things, here's a packet sniff of all of the data that's currently flowing in the nearby area, and you can actually infer from some of the source names that there's a whole bunch of people have Apple hardware that is broadcasting in this area. Intel Core, whatever that is. I saw mention of Barnes & Noble earlier, which means we were picking up some kind of, actually we're probably picking up a Nook or something like that, or maybe the Coops, because they're owned by Barnes & Noble across the street. But it's this easy. Download free software. This is actually called Wireshark, and turn it on, listen in what's called promiscuous mode for reasonable reasons on your computer, and it listens to everything, even if the data is not meant for it. And I do actually mean this. Don't do this on campus. Play with this at home with your own wireless router. But one of the protocols that you see quite a bit in that middle column is ARP. It's actually pretty innocuous. ARP just refers to computers trying to figure out the IP address of some other computer. For those interested in networking, you could take CS143 as well as a couple of follow-on courses. But as you can see, there's not all that much traffic in the nearby area because Wi-Fi here is so limited. You would see much more in other places and much less if data were actually encrypted. But as some of these lines see, we have at least one HTTP there. Here's an actual TCP packet. And if we were really nosy and bad people, we could start diving in deeper to these packets and see what the actual instant message was, emails, or the like. So it's this easy to actually sniff the data that we take for granted is more secure. And FTP. This is kind of an easy one. What's FTP? Yeah. File transfer protocol. So it's like SFTP, literally without the S, without any notion of security. And this is actually a real issue too, because if you're starting your own website and you're not just using FAS or the cloud or whatnot on campus, and you're actually paying a third-party web host, not all that many web hosts actually have SSH and SFTP. A good number of them still use, even if they don't use Telnet, they still use FTP, which means anytime you're updating your commercial website and all of your intellectual property, it means you're sending your username and password across the entire internet just to log in. So there's absolutely no reason these days to use FTP over a public network. All right, so how do we start protecting code on what's a shared system? So when you were using the CS50 appliance for the first couple projects, you had the luxury, of course, of being the only one using that appliance, but that's not a common model. So if you used cloud.cs50.net, or if you use DreamHost or some third-party web host, odds are you're not on your own dedicated server, but you're on a shared web host where a whole bunch of customers have usernames. So let's think this through. If I have Alice as a username and Bob as a username on a system, and both of them have websites written in, say, PHP, how do I want to chmod my files typically on a web server? What should an HTML file be? Start easy. OK, 644, which means readable and writable by me. It's 4 plus 2, so read plus write is 6. So that's me, and 4 means readable by everyone else. So that's good. And a GIF and a JPEG, same thing. CSS, JavaScript, same thing. PHP gets a little more interesting. So we don't have to worry about those other formats all that much because they're by nature designed to be publicly accessible. I have to see the GIF. The browser has to render the HTML. But PHP could have, a work that could have the results of my hard work and intellectual property and thousands of lines of code that I certainly don't want to turn over to anyone on the internet. Might have usernames and passwords to connect to databases or APIs or the like. So probably not good to chmod your code, your PHP code, 644, right? So 600, which means only I can read and write it, is probably a better thing. But what does that then mean for the system? That means that the web server has to be able to read my code. But if 600 means only I can read my code, feels like my code is now super secure because not even the web server can serve it up. So how do we mitigate this? Yeah?
The SuPHP module will run,
Oh, wonderful, clever answer.
will run the code as your user.
Good. So we did use in the appliance, we do use on the cloud, and some web hosts, but not many, use something like SuPHP. There's other versions of this, FCGI, FastCGI, and there's a couple of other incarnations of this, but it does exactly that. SU is substitute user, PHP, and all this means is that this is a free module that you can add to Apache or other web server packages that make sure that your code runs as quote-unquote Alice or as Bob, whoever you actually are. So this way, your code cannot do bad things to other people's code. So under this model, if I'm Alice and my code is executing under username Alice, that means my PHP files only need to be chmoded 600 because only Alice needs to read those. And if the web server is pretending to be Alice, then that's perfect. Only Alice has permissions. But if now Alice is trying to be malicious and tries to overwrite files in Bob's account, she won't be able to, right? Because her code's executing as Alice. And so long as Bob hasn't done something stupid, like chmod his file 777, and if you've ever done this, and you know who you are, not the best decision, that means anyone on the system can write to your files. And so all Alice has to do is know or guess some file name. And if your file name is called config.php, and that's where all your usernames and passwords are, it's not going to take Alice all that much time to somehow gain access to all of your files if there weren't this defense of everyone operating under their own username. So actually looking for web hosts that do support this or the equivalent so that your code is only running as you, or you have a dedicated server so that yours is the only code running, is certainly something you should be mindful of. Another alternative, not uncommon years ago, well, if the problem is that you want your files owned by and viewable only by Alice 600, but the server needs to see it, well, a solution here would be to run the server in administrative mode. So have the server be run as root. Okay, it's not done as often anymore, but why is this bad, probably? Yeah?
Now there's a vulnerability in the server, you're able to access all of the system's files.
Yeah, exactly. Running anything as root is generally a bad thing, right? Because if there is just one bug in Apache or in PHP or whatever tool you're actually using, and some bad guy on the internet figures out how to exploit that, the account that he or she has just exploited is, of course, root, which now means your whole machine is hosed. And this has non-trivial implications. When you detect your machine has been compromised, you can't just like upgrade PHP and say, okay, now I'm safe. You have to assume that every aspect of your machine has been compromised, and you literally want to wipe it and start from scratch. The data you can pull off, but any program like the login program, the SSH server, the web server, you should assume that now they all have a backdoor of some sort that the bad guy put in there. In fact, years ago, the first way I learned this lesson was I was living after college with some roommates, and we were running our own Linux server for file serving and print serving and for internet access. And I woke up one morning to print something, and all of a sudden I couldn't print. And this was kind of curious and suspicious, but not worrisome at first. But when I started poking around, I realized that our Linux server no longer had a /var directory. And /var means variable. It means where stuff is changing on a system typically. But in var is /var/spool, which is the mail spool, which is the folder in which files to be printed end up. And there was no var directory anymore. But what else is in the var directory typically on a Linux box? So var www is often there. And what else? Not passwords. Those are usually in etc or /etc or elsewhere. But var/logs. So what this bad guy had done, and to this day I don't know what exploit he or she took advantage of, but their approach to covering their track so that I wouldn't notice the machine was compromised was to rmrf/var, and with it all of the logs, and of course with it the ability to print, and so that was our tell. And I wasn't very good at auditing things at the time with special tools and whatnot, so the mere fact that I couldn't print, inability to print should not be your first clue that you've been compromised. So realize that keeping these things in mind can have some real repercussions. All right, so any questions on these sort of lower level details of ownership and things to be mindful of when moving from classroom to real world servers? All right, so this one's fun, if only because it involves this guy. Cookies are sort of this fatal flaw potentially in a lot of websites. And we did a fun demo a couple years ago, talked about it in 50 this past year as to how you can exploit these things called cookies. So in general, all of these lines of text, this represents what? What did I copy and paste here? Yeah, so it's an HTTP header, a set of HTTP headers. And are these from the server or to the server? From. And how do you know? What's the tell? What's that? Good. So the 200 OK is something a server would say, not something a browser would say. And also a server would say set cookie. A browser would only say cookie. So a couple of clues there. So in bold are a couple of cookie values. The first represents what? Yeah, so it's a session ID. So you know that in PHP and in other languages, you have this notion of stateful information, whereby you have some global variable like $_session in PHP that you can read and write values to. And somehow or other, those values come back to you and are still available to you, the programmer, even after the user has just loaded a page, walked away for 10 minutes, and then clicks on a link and visits some other page entirely, even though the connection, the TCP connection to the server, was broken. So why is this such a long sequence of numbers and characters? Why not just say the session ID is Malin's? Just ask kind of a dumb question. Someone else. OK, yeah.
Because you could just write your own cookie file on your computer or change the value of that one to whoever you wanted.
Right. Right, exactly. You don't want to pick something that's so deterministic and so obviously identifiable that anyone could spoof it quite easily. Even though we take for granted that the browsers are sending these things back and forth, in 1 minute you could write some PHP code that mimics these same headers and then pretends to have any cookie value it wants. This is generally known as session fixation, just fixing the session to be some known value. So this is probably some huge pseudo-random number. And path at the end just means it's valid for foo.com/, so the entire domain, for instance. So this is all kind of a big problem, though, because even though this number is big and pseudo-random, I'm not likely to guess it. But we just saw with Wireshark that I could very easily, within seconds, sniff any one of these session cookies if people are on Facebook or on Gmail or the like, and then present it as my own, potentially, thereby logging in as your account. Firesheep was the tool that came out about a year ago that made this all the more evident to normal people because it was so easy all of a sudden to do this. So how do you prevent things like Firesheep? How do you prevent random people like me sniffing a cookie, then pretending to have that same cookie so that I effectively can log into whatever website you are currently logged into as well? Thankfully, this one actually has a right answer. Yeah. Yeah, so encryption. So not always, but often encryption at least is the answer, or at least raises the bar to these kinds of things. So we're all seeing this in the clear, but if you just encrypt all of this information, now only browser and server can see this, and so that actually does prevent this attack. I don't know, has Facebook switched over 100% to SSL, or do you still have to opt in? Okay, so that's curious. So at least everyone in this class, frankly, should opt into this feature, and I'm sure it's buried somewhere under settings or whatnot. But if you go home tonight or right now and are playing with Facebook and you see that your URLs are all still http:// not just for login, or not for login, but for everywhere else, go find this option, because it means all this time your roommate or some random person in Starbucks could trivially be logging into your Facebook account. Gmail's better at this because Google a year ago switched over to SSL as well. Some websites are starting to do this, but why would not every website do this? Yeah?
It's more heavy for, like, it's more, it has to do computations.
Yeah, so it's a little more work for the server. If you assume that no cryptography is free, but some cryptography requires some CPU cycles, and you only have a finite number of CPU cycles per unit of time on a server, right? It's 1 gigahertz, 2 gigahertz. If you're going to spend some more of your cycles on encryption, it means you have fewer cycles available for more users. So if you previously supported 100 users, now you might support only fewer than 100 users. Is that reason enough to make all of your users vulnerable to this? No, probably not. And to be honest, in the commercial world, there exist devices that called SSL offloaders that you do all the encryption for you, so you don't have to worry about pinching pennies in that way. You just have to buy 1 or 2 such devices. So this is something, too, that frankly, moving forward, all of your sites should operate over SSL. I mean, even the courses, CS50s, all of our stuff, almost all of our stuff now is over SSL because it's so easy to do. And frankly, not until you get to the point of like Facebook and Google and Twitter where you really have to worry about saving every little CPU cycle is this probably a financial issue anyway. All right, what about this other set cookie? This suggests a vulnerability or a poor design decision. What has this developer apparently done? How can you remember that a user has logged in to a website? Poorly, let's say. So you can just plant whatever they typed into the password field in a cookie and just ensure that every time the browser revisits the page, here's my password, here's my password. Is this such a big deal over SSL? You know, maybe not, but is it necessary? Probably not. You should generally minimize the number of times anything important goes across the wire, and of course the session ID should obviate the need for that, because that's the number that should be remembering that some user is logged in. Yeah?
So, quick question about encryption. So, I know that the way you talk about it is that we should, trust across the board. Are there any vulnerabilities to websites that claim to use SSL without using properly? Like they don't do the certificates right, or they're getting spoofed in that way. Is there anything we should look out for?
Oh, good question. So things to look out for even when using SSL. So actually, let's come back to that in just a moment and then dive in deeper with the crypto itself. And for now, let's just finish up this one thread with session hijacking. So this is the Firesheep stuff for those familiar with that particular tool. So how do you go about stealing someone's session? Well, you download Wireshark for free, you turn your computer into promiscuous mode, and voila, you have all of the HTTP traffic flowing locally around you, and you can just cherry pick all of the session IDs you want. Or even easier, you download something like Firesheep, which does all that work for you and just gives you a list of Facebook faces to double click on to log into that person's account. But what about physical access? If anyone ever has physical access to your computer, you're kind of screwed. Like whether it's a Mac, PC, server, or whatnot, because even Linux servers, for instance, which might have root access and separate user accounts and the like, as soon as you walk up to a physical machine, you can generally either reboot it and then type a command into what are called the kernel parameters. For instance, in Linux, if you play with the appliance and you hit escape at the right time, and then you hit E for edit, and then E for edit again, and you type in the word S or single for single user mode on a Linux server, server. That gives you unrestricted access to the entire system, loading to the blinking prompt without even asking you for the root password. And that simply requires physical access. On some servers, you might think, oh, but I'm super paranoid. My PC in particular has a BIOS password, so you can't even boot the computer without a password. Yeah, well, if I look up the user manual and I figure out what jumper I need to touch inside your motherboard, I can remove the lid of your computer. I can take a tiny little piece of plastic and metal, make it close a circuit between two little metal pins, and that will typically wipe out whatever BIOS password you have. Now, why is that useful? Well, there's a lot of humans that forget their BIOS passwords, so that's the way to reset them. But if an adversary knows this, again, you're kind of screwed. So physical access, bad. But also, of course, hard to prevent against. Yeah.
And encrypting your entire computer wouldn't do anything either.
Encrypting your entire computer. So that's definitely compelling to encrypt your computer, but when you're using it, the information obviously has to be decrypted. So right now, for instance, if you are using File Vault on a Mac and even secure virtual memory, so long as your lid doesn't close and the password's not forgotten, now I could access anything on the computer, but using full disk encryption, absolutely good. And in fact, as an aside, unrelated to websites and such, if you have a Mac in this room, go find the option sometime tonight or soon and turn on full disk encryption. And if you're really paranoid, secure virtual memory, which also encrypts your use of RAM, so that if your laptop is ever lost or stolen, it's at least the hardware that's gone and not sensitive information you don't want someone else to see. PCs, frankly, Microsoft has never made this easy. You have to generally buy some third-party product to do this. Yeah?
Are there any performance drawbacks to that?
Yes. Are there performance drawbacks? Yes. None of this stuff comes for free. You have the crypto involved, but frankly, on machines these days, it's probably a price worth paying unless you truly have nothing that you care about on the computer.
Can you repeat those two options for the Mac?
Sure. The Google File Vault, one word, and then Google Secure Virtual Memory. And I think if you go to System Preferences and go to Security, you can do it there. But two caveats. One, don't do it in class, because if you close your lid, bad things happen. If you lose power, bad things happen. And I would generally back up before, just because when you're encrypting your entire hard drive, if something does go wrong, you will just be left with a sequence of random bits. But this has its advantages. Those of you who have iOS devices, if you've ever wiped the device, if you had iOS 3, and I don't think 4, but iOS 3, it would actually take a long time to wipe the device because all of the bits would be overwritten with zeros and ones and the like. And that was a good thing if you wanted to sell the phone or give it back to the Apple Store and you didn't want anyone getting your emails or any sensitive information that was on there. But now you can wipe an iPhone or an iPad actually within seconds or maybe a minute, much, much faster, even though the device might be 64 gigs. How do you do that? How do you still wipe a device effectively, but do it much quicker than apparently they previously did?
You just wipe the hashing again to decrypt everything?
Yeah, so you wipe the key that's being used. So if you keep the entire device encrypted all the time, which does have a computational cost and might slow things down some percent, well, if you want to wipe the device, all you have to do is overwrite with zeros and ones just the key that's being used to encrypt the entire device, like the password that you typed in to unlock the device, because as soon as you lose that key, by nature of encryption, if it's a good encryption algorithm, all of your data will appear already to be random. It's not going to be all zeros, but it will at least be a random sequence of zeros and ones if the cipher is in fact probabilistically good. So that's a good thing. Crypto is actually quite cool. And if interested in this kind of stuff, CS221, generally taught by Michael Rabin, Turing Award winner, is a fascinating class to take on the subject. RJ.
So if you do this file vault thing and you encrypt your hard drive, and then an OS file gets broken in some way, is there a way to get back to your data, or are you kind of screwed with that one?
Good question. If your data is encrypted and something goes wrong, the bar has been raised to getting it back, yes, in fairness. So in this case, backups are good. And even now, Time Machine, which comes with Mac OS, can support backups that have been encrypted with File Vault. So there, the best solution is backups. And sorry this is so biased toward Macs. It's just Apple has done an amazing job at making this easy, and Windows, for some reason, has never made it as simple as a menu option. Maybe that'll change in the next version. All right. So if you're doing sketchy things, get a Mac, I guess is the takeaway here. All right. So other things you can defend against. So physical access, you can only do so much sometimes. How about packet sniffing? So how do we actually prevent someone like me from doing what I was doing with Wireshark there? How do you actually hedge against this risk? Because if you're in an airport, you're in Harvard. I mean, Harvard's access points are all over campus. We could certainly sniff a whole lot of data. Don't. What could you do, though, to defend yourself against that kind of attack and the stealing of your cookies and the like?
Use a VPN.
Yeah, so you could use a VPN. And even though this might seem a little silly, you could be on Harvard's network, VPN to vpn.fas.harvard.edu, so that at least you're protecting yourself against all the random people near you wirelessly, and now only exposing yourself to risk by people who have physical access to the network, which are more likely to be sysadmins, people in the physical science center, or still random people on the internet, certainly. But odds are you might be more concerned just by nature of the threat you're concerned about your roommate or people who actually know or care what you're actually saying on an email or an instant message, whereas everyone on the internet probably doesn't care too much about what you're doing. So vpn.fas.harvard.edu is something you can all sign into, and it's actually good if you're on in an airport, in Starbucks, or in another country that doesn't let you access certain sites. You can pretend to be on Harvard's campus that way. Other tricks? Yeah.
If you're really crazy, you can use Tor.
Okay, so Tor. What is Tor?
Tor, I think it was developed by the Navy, but the idea is that there are different nodes that exist all across the world.
Mm-hmm.
And so when you send information, it sends it to a random node somewhere else in the world. So unless you somehow did statistical analysis of the entire internet, you really can't figure out which packet was sent where by what computer.
Good. Yeah. So Tor, to summarize, is a distributed proxying service, and it's a system sort of like a peer-to-peer network. So random people can download the Tor client, run it on their computer, and then they become a Tor node. And it's used in exactly that way. If you want to do something privately or statistically securely, you can use the Tor network so that your data, much like in the movies, frankly, is routed from here to here to here to here to here to here to here, finally to the endpoint, because it's then much harder for people to actually figure out what your origin is, because the data is going to be coming from some random person's computer here, and even if they go look at that computer or subpoena that human, then they have to trace it back one step to the previous computer, to the previous computer, to the previous computer. So it's actually a relatively effective technique for anonymizing your traffic. Of course, you have to trust all of these middlemen, and there's nothing stopping the government from being one of the Tor nodes and being one of the partners in this relationship, but at least it's a mechanism. It does tend to slow things down, though. Other tricks that one can employ? At least at home, you can use something like encrypted access points. And Harvard doesn't do this, probably either for performance or just convenience. MIT, though, has a secure version of their network. Other universities do as well. The only gotcha there is that you can have a WPA2, or WEP is bad, WPA2 encrypted network. But what's the gotcha? Because it's not obvious that Harvard's doing anything wrong here. Because if we do use encrypted Wi-Fi, what's the implication for users? If we want all of you to still be able to connect to the encrypted Wi-Fi, we have to tell like 30,000 Harvard affiliates what the password actually is, so that's not necessarily raising the bar all that much. I mean, some schools actually just post it on their website so that you at least have to know what you're looking for, but there are enterprise solutions as well. But it just gets harder to do that. So thankfully, clients to do this end to end. And we'll come back to this last one, XSS, in just a moment. So quick look at SSL. SSL is all about HTTPS and about encrypting things end to end. What does it involve if you want to start your newcompany.com and you want to run everything over SSL? How do you make that happen? What's step one? Yeah.
You've got to purchase a certificate from a trusted authority.
Good. So you have to purchase a certificate from a trusted authority. You can do this from a whole bunch of places. One of the places that's relatively cheap, though there are even cheaper places, is GoDaddy here. For instance, if we go to SSL and security, and we scroll down here, you'll see that you can get standard SSL for $69 a year or premium SSL for $99. What's the difference, as best you can tell?
There's a green box around that.
Yeah, so you get this green box. So that's literally it. So for $30 more, you get a green box around your URL. And this is because the browsers, there's some merit to this idea. Some browsers decided that at least to raise the bar so as to make it more obvious to users that this is a legitimate encrypted connection to a legitimate website, you can pay a bit more, and certain browsers like Firefox, for instance, will turn the URL a different color, signifying really that these people paid more and also that we, in theory, vetted them more. So you didn't just automatically get an SSL certificate after giving a credit card number, which might be stolen. They do a bit more due diligence and try to figure out if the person ordering the certificate is who he or she claims to be. Crypto-wise, what more do you get? Well, apparently you get like $250,000 warranty with $99 versus only $10,000 warranty. Now, if you ever read the fine print, this is kind of meaningless, right? This probably says something like if the RSA algorithm is cracked, like we will give you this much money versus this much money, which is not likely to happen. And even if it did, they're not likely to pay out, certainly given how many customers they have. So in short, paying for more expensive certificates, generally kind of dumb and unnecessary, at least for websites that aren't banks and don't really have the money to just throw on at things like this. I mean, out of curiosity, how many of you knew before a minute ago that green meant something more? So 1, 2, 3, okay, so like 7 or 8 people. Okay, so the $30 is to make those 7 or 8 people happy. And of those 7 or 8 people, how many of you would not visit a website whose URL is in green? Right, so I mean, what's the point, really? So nice idea, but hasn't quite gotten popularized. Now, if you want real security, you can go with a brand name like verisign.com. And if we go to VeriSign and I go to SSL certificates, which a lot of companies do, get redirected here. And let's see. Oh, you know it's going to be cheap when they don't even show you the prices. So let's see. This green looks good. So let's go. This is Secure Site Pro with EV, extended validation, whatever that is. $1.5 million warranty. That sounds amazing. So let's go here. All right. How many years? We'll just do 1 year, 1 certificate, organizations. Okay, don't need another name. Don't need them to contact me. Ooh, there it is. $1,400. Not bad for the same exact math that we could have gotten from GoDaddy, and you can get it even cheaper at other places as well. And technically, you can generate certificates yourself. And that's actually the only bad option, at least for corporate websites. So what's really going on here? So how does SSL work? Well, if you're generally familiar with public key cryptography, there's 2 keys involved in this encryption process. The browser has a public and a private key, and the server has a public key and a private key. And thanks to very nice math, and we'll take a look at a representative example called Diffie-Hellman in a bit, thanks to very clever math, Alice can ask Bob for his public key. Alice can then encrypt information with Bob's public key and send it to Bob. And in theory, no one who intercepts that message should be able to decrypt it, because the only number in the world that should be able to reverse the effects of Bob's public key is Bob's private key, thanks to a nice intertwined relationship between those numbers using something like RSA, or in the case we'll look at, Diffie-Hellman. And then Alice and Bob can communicate conversely in the opposite direction with Bob using Alice's public key. So this is great, because this means when I, a user, visit Amazon.com and check out for the very first time, I obviously don't know anyone at Amazon, I might not have visited their website before, that's okay, because as the name suggests, a public key can be transmitted in the clear, can be shouted verbally to the whole world, because its only value is for encrypting information, or, as an aside, for digitally verifying something called a digital signature. More on that in 221 and the like. So what's the relevance here? Well, if I have a public key and a private key, and Bob has a public key and a private key, it's not enough that we just have these big numbers that we can use for encryption. The idea behind SSL is that there's this whole chain of trust. And ideally, I only want to trust Bob's key if someone else has vouched for him. And in that case, it's someone like GoDaddy, or it's someone like VeriSign, someone who's at least raised the bar to say you are who you say you are, you own this domain, is really the vetting that they do. Or in the case of the pricier ones, they might actually ask for some kind of corporate document demonstrating that you are who you say you are. And this way, this is what you're paying for. You're getting a stamp of approval from someone more important than you, like VeriSign or GoDaddy, or bigger than you, that says, as an authority, you are who you say you are. So if I instead just generate my certificate myself, my public-private key pair, and start using it, what happens generally on the web if you're using an uncertified key pair? What does the user see? Yeah?
Well, I'm just saying it's vulnerable to random attack.
Okay, so yes, SSL is still going to be vulnerable to something called man-in-the-middle attack. So let's come back to that in a second. But what does the user see if you haven't paid for a certificate? You've just generated it yourself. Yeah? Yeah, so Firefox makes this look really scary, right? Firefox is atrocious. You have to click like 5 different buttons just to get past a site that has not paid for its certificate or whose certificate has expired. And I don't know if I can... There's annoyingly some websites on campus. Let's see. Let me see if I can find one off the top of my head. No, that doesn't even work. That's nice. Oh, it's also because I have no Wi-Fi. All right, so we're very secure right now. All right. So there are a non-trivial number of servers on this campus who shall not be named that haven't paid the like $69.99 to have a certificate for that website. There also, frankly, exist wildcard certificates, which means for $100 or $200, annoying, but cost effective in the long run, that can secure an entire suite of subdomains. So CS50, for instance, and even 164 paid for the wildcard certificate, so we can have as many subdomains as we want. But the real takeaway here is that SSL, to some extent, it's nice by theory, this construction of this chain of trust, but it's also a bit of a scam, and it's a bit of a marketing mechanism that's been put in place. And the fact that, frankly, we as a course need to literally pay another $200 every year to renew the certificate just to have GoDaddy, of all people, say more authoritatively that we are who we say we are, is kind of become a business unto itself. But it's worth paying for so that your users don't have to jump through those hoops of user interface to actually proceed to the next screen. So in short, that's what's going on with SSL. But there's some fascinating work, and I'll try to post on the lectures page tonight or tomorrow a talk someone gave that makes pretty clear and pretty accessible just how easily SSL can still be compromised. All it does is raise the bar, but it's not the end all. Any questions on SSL? All right, so let's take a break, and then when we come back, we'll take a look at some scary looking but very sexy math. That'll get you to come back. All right, so we are back. So public key crypto, as it relates to browsers or really any mechanisms that's using public key crypto, even if it's something like email and PGP for encryption, works by, again, having these asymmetric keys, public key and private key. And RSA, as you probably heard, is quite common. But there's another algorithm. There's many other versions of public key crypto. But one of the easiest ones to explain as a first pass is something called Diffie-Hellman. In this case, this is a story that goes in both directions simultaneously and actually hopefully will give you a sense of how relatively accessible the kind of math is, even though the numbers involved are quite big. So on the left, let's assume that Alice is standing. On the right, Bob is standing. And these two want to communicate securely. Of course, they can't just pick a secret key like the number 13 because they would somehow have to both know that the secret number is 13. And that's fine if they can chat in advance. But obviously, if Alice is Amazon and I'm Bob, we can't talk in advance as to what our secret's going to be. So we have to use something like public key crypto. So Alice and Bob in advance are going to publicly agree on two numbers, G and P. G is what's generally called a generator. In practice, it's often just the number 2, though other possibilities exist. But there's some nice properties of 2. And P is a prime number. Now, in this case, P is generally a very large prime number. But both of them have to agree on these numbers, and they can shout them across the world. Everyone else in the world can know that they're using these numbers, as well as using Diffie-Hellman. In fact, as an aside, one of the key principles of security is that security through obscurity, like not telling anyone what algorithm you're using or not telling anyone what some of the inputs to your program are, is generally not best practice. Because if the security of your algorithm just relies on secrets as opposed to complexity, all it takes is for one person to spoil the answer for someone. Whereas a computational complexity requires time. All right, so they agree on these two numbers, G and P. Again, number 2 probably, and a big prime number. And then Alice and Bob each choose one random number, big random number. Let's call it A and B respectively. Then Alice does some math. She computes the value G to the A. So this is 2 raised to the A power modulo P, so exponentiation. Now, whenever you take an exponent of something, especially large numbers, this thing can get huge fast. But if unfamiliar, know that there's actually very nice ways of doing modular arithmetic whereby you can actually raise it to a power, but not A, raise it to a smaller power, then do a mod, then another power, do a mod, then another power, so long as those exponents ultimately equal A itself. So there's nice ways of doing modular arithmetic so that your number doesn't get too huge before you do modulo prime number. So that is to say, it's actually pretty easy for Alice to compute G to the A mod P. So just so we have a variable for it, let's just call that TA, T sub A. That is the number Alice computed. Alice sends that across the wire. So that's what's denoted by this arrow here on the very top. She sends not A, not G, not P. She sends the computational result of that expression. So Bob does the same thing, but he does it with B. So at this point in the story, Alice has A, and she has G to the B mod P, aka TB, whatever that number actually is. And Bob, meanwhile, has B and what Alice sent him. Well, now, thanks to the ability to multiply exponents, you can actually now compute the same value at both sides. So Alice, upon receipt of G to the B mod P, she takes that whole value and just raises it to the power of A, her number, and then does a modulo p again. And thanks to nice mathematical properties, what she really gets then is g to the a times b, or equivalently g to the b times a mod p. And Bob, meanwhile, gets the exact same results. So it's done in the opposite order, but the product ultimately is the same of those exponents. So at this point in the story, Alice has a secret number A that she did not send across the wire. Bob has a secret number B that he did not send across the wire, but both of them magically have this big number, g to the a times b mod p. So what then is going to be a number that they can then use securely? Well, they have effectively come up with a shared secret. So much more sophisticated than a Caesar cipher number of 13. They now have a nice, big, seemingly random number to use that never went across the wire. So this is, in a nutshell, how you can use public key crypto to exchange information securely. They now have a shared secret. RSA is a little more sophisticated, but again, if you're liking this kind of crypto stuff, do shop at some point one of the higher level CS classes. All right, so now let's come back to a story that we hinted at earlier, and some of you might have seen, so we'll do this one somewhat quickly, but it's nonetheless always fun. So suppose you want to log into a website, and you're not supposed to. One of the fun things to do when you're bored is to try to see if the website breaks if you type in some bogus characters. In fact, if you want to try to exploit a website, what are some good characters to type into the username and or password fields of that website? So null characters. So you can actually somehow copy and paste null characters, which you can get from like a sophisticated text editor, for instance. So you can just paste those in, which normally you couldn't type easily. Even simpler. What else is juicy? Parentheses, single quotes, semicolons, double quotes. Generally, quotes are a pretty good bet, because if the website is using SQL, they probably do have some quoted strings in their queries. And if they didn't have the foresight to actually scrub user input, you might actually trigger an error. And this is where adversaries get their advantage. I don't need to compromise this site in the first 5 minutes, but as soon as I get it to crash or yield some kind of server-side error message, that means someone screwed up. And then I can focus my attention and my interests and my spare time all the more deliberately on this site and figure out, well, what sequence of bogus characters should I type in to do more than just crash the server, but rather to somehow take it over or steal some data. So in this case, here's a very common example, and some of you, if you went to Hack Night recently or last year, you've seen this example before. This looks completely ridiculous, and I actually artificially removed the bullets that would generally appear in the password field. But suppose a user does type in single quote, space, or space, quote unquote, 1 equals quote 1, but no close quote. So notice the awkward asymmetry here. I start with a single quote, but I don't end with a single quote. And that's because, on a hunch, I feel like whoever implemented this website is probably doing a query like this. And this is one of the more simple approaches you can use in PHP. The goal here is to generate a SQL string. sprintf is like printf, but it returns a string rather than printing it to the screen. So select user ID from users, where username equals quote unquote %s, and password equals quote unquote %s. So that feels reasonable. But if what I then plug into those placeholders is literally what the user submitted, very bad. Right? So if I have not scrubbed the user's input, they could have typed anything, including that cryptic sequence of ones and equal signs and single quotes. And if you think about what I did type, I started a single quote, but I didn't end with a single quote. So whatever I typed in is going to end up where this %s is. And I didn't even type in a username. So if I now do that substitution, what does that query become? Well, it becomes this. And what does this where clause evaluate to? It's a sort of a vacuous truth. It's always going to evaluate to true. So what am I going to get back? I'm going to get back a whole bunch of UIDs. In fact, all of the user IDs. And if the next lines of code in the program are only checking for the presence of one or more user IDs or no user ID to determine whether the user exists, well, odds are I've just maliciously logged in to the poor guy whose UID just happened to be first in the result set, the very first person to log in. And maybe that person doesn't even use their account anymore, so now I'm into a fairly dormant account. So what's the solution here? Well, clearly the fact that I was able to finish the developer sentence, so to speak, with those SQL queries was not the best decision. So it's a ridiculous function in PHP, but this is one way you can do it. MySQL real escape string, which pretty much puts backslashes behind any potentially dangerous characters, among them the single quotes. So what that query would look like if we escaped it is something like this, which is actually hard to parse visually, but it's actually now safe. All I did was escape the single quotes that the user actually typed into that password field. So it's this simple, but clearly people make this mistake. And in fact, I was just reading today, and I didn't look too closely at the article, but this outbreak of the Mac worm that everyone's been freaking out over seems to have been popularized in part by compromised WordPress blogs, and it always seems to be WordPress or Joomla or these very popular CMSs and such that infect the world with everything because they use stupid functions like eval. They don't have escaping going on all that often, but it's so easy to forget these things. So indeed, one of the things we talked about early in the semester, PDO, one of its most compelling characteristics is not just the abstraction you get between using MySQL or Oracle or the like. It also does all of this stuff for you. And that's huge, to just distrust yourself. So getting into the habit of not using raw PHP functions like this, but actually using a library where you can assume or at least trust that someone else has given this more thought than you might is probably your best defense. And to stop thinking about escaping, but punt to a library that's going to do it for you and do it correctly. Super easy to do. So lastly, and Yella pointed one of these out before. So there's actually two attacks when it comes to web security that are actually a little non-obvious, but you hear these buzzwords tossed around a lot, perhaps because so many people are in fact vulnerable to them. So cross-site request forgery, sometimes written with an X instead of a C. So here's the scenario. You log into something like eTrade.com. You then go to some other bad guy's website, but that bad guy has a link back to eTrade.com, and it uses a GET request to essentially trick you, into this case, into like buying a share of a stock. So in other words, you go to eTrade.com, you log in, therefore you have a session cookie with them. And just because you leave the website doesn't mean that session cookie expires. In fact, it might not expire for an hour or a week or a year. So you're still logged into eTrade, even though you're not physically seeing that page. So if you somehow go to this guy's website and click on that link, you've just been tricked potentially into buying a stock on the other website. And you don't even have to click a link, right? He could just do an HTTP redirect on you. It could be in a form submission. He could have, even more cleverly, this tag embedded, for instance, in any of these, which is super clever. Things that you wouldn't even notice or see, right? All of those would trigger an HTTP GET request to some other website just to see if that website is vulnerable. So how do you defend against this attack? And indeed, those of you who took 50 and did CS50 finance, odds are you didn't really defend against this attack, albeit with your fake eTrade-like site. So how do you defend against this attack, which seems so relatively easy to wage against your users? Yeah?
Can you generate a random key every time you load a form on your own site so you know that the request is from your own website, not from somebody else?
Good. OK, so you can kind of have some kind of seed value, some kind of hash value that has to be resubmitted with the stock purchase that a bad guy's random website would not know because it's constantly changing. But if you actually did commit this buy on the real eTrade.com, that would be a hidden form field that comes with it. So a kind of a token, a temporary token. So that could be one defense. Now, of course, the bad guy could really be malicious and somehow sniff that cookie. But let's assume our adversary is not sniffing all of our traffic. What else can you do? Yeah, Kevin.
Could you make people like re-log in if they want to buy this stuff, or like when they get to that link, have them read?
Good. Yeah, so I'm kind of being unfair to eTrade. Odds are they don't have like one-click stock purchases features, right? Where you just send a GET request and you buy the stock. Odds are they'll prompt you to at least confirm, or even more securely, prompt you to re-log in. In fact, if any of you shop on Amazon.com, it's a little annoying, but they do exactly that. And every time you add stuff to your cart, you then check out, and then they prompt you for your password again, even if you just typed it in. And that raises the bar. What else could you do here to defend this? There's kind of an obvious one, even though it's not perfect. Yeah?
You can check the refer, but that's not very secure.
OK, good. So you can check the HTTP header, the HTTP referrer header. But indeed, that can be very easily spoofed. It can be scrubbed by browser privacy settings or special proxy software. So good as a heuristic, but not as something to rely on. Good. So if the whole problem is that gets are just so damn easy for other people to construct, well, let's just use posts instead. Now, of course, that would fix, in this case, all of these attacks. All three of these links would now no longer work if we only supported post. But anyone who knows a little bit of JavaScript can actually trick you into submitting something via post, and can even redirect you via post by having a little JavaScript event handler that says as soon as you're on bad.guy.com, do form.submit, open paren, close paren in JavaScript, and bam, you've just submitted a form via post elsewhere. So it does raise the bar and makes these kinds of attacks harder, but doesn't solve it perfectly. but in conjunction, pretty good things. But really, again, I would propose that the takeaway here is that if you never even thought about what could happen if someone else tricks a user into following a link like this that you were just taking for granted for yourself, like that's really the takeaway, to at least give some thought to this and then decide, is it really worth my spending the time and effort to raise the bar even further? So this is the XSS type attack that Yella referred to earlier. So this is unfortunately a little hard to fit in a big font, but if we look at the top line there, so vulnerable.com means this is a poorly designed website, and suppose that it has some URL that expects an HTTP parameter called foo, and foo gets its value from like a form field or something like that. Well, suppose that the bad guy types in literally this, open bracket script, close bracket, ... But the interesting part of this is that what is he doing? He's doing document.location, so that's going to change the URL to be what? badguy.com/log.php. So in other words, I'm going to redirect the user from the vulnerable site to my bad guy's site. But what am I going to pass in just for fun? The contents of the user's cookie jar. So document.cookie is the user's cookies for the current website. So that means the badguy.com has now logged, presumably via log.php, all of the cookies. So what's probably among those cookies for vulnerable.com? My session cookie, or God forbid a secret, like 1, 2, 3, 4, 5, but probably my session cookie, which means badguy.com doesn't even need to be in Starbucks with me. He can be anywhere in the world and now log into my Facebook account, Twitter account, whatever it actually is that is vulnerable.com. And how about here? This is just to make clear, actually what the user might see is this, which makes a little less obvious what's going on, just because no one can understand things like the % signs and the URL encoding there. So not very good if the user can actually hijack your cookies. Other questions? Oh, and so as an aside, this is commonly seen, and I think even in 50 I did the demo where I didn't type in a document.cookie example. I think I did something like alert, and I said hi on a web page. Obviously, hi is not really an attack on a website, because if you trick the user into triggering JavaScript pop-ups, annoying, but not dangerous. But again, increasingly do websites contain juicy information within the scope of the DOM itself, and that information can, in fact, be leaked quite easily. Any questions? All right, so a lot to think about. Not directly applicable necessarily to iOS projects unless you are doing things on the back end, but certainly moving forward as you exit this course, keep in mind how better to engineer your software. So on a sad note, we're almost done. The SES Design Fair is next Tuesday. This is meant to be an event across Cs, CS50 in spirit, but done more on a course-specific basis. We are slated to be in the ground floor of Maxwell Dworkin with a whole bunch of bar height type tables. There'll be food and music and the like, as well as classes like 171, 179, 51, some engineering sciences classes. This will be next Tuesday, which is a couple days before the last iOS project is done. So the goal, let's say internally as a class, is to impress everyone else, even if you know there's menu options that don't yet work on your application. That's totally fine. You can now learn the delicate art of presenting things only that you know to work. But it's OK if not everything is done by Tuesday. And Tommy and Rob and I will send out an email sometime this week dividing the class up into 3 shifts, much like the CS50 fair. And the goal is really just to come for a bit, couple hours, hang out, socialize, eat, show off projects, and also see what others in the engineering school have done. So without further ado, that's it for CS164. Thanks very much. We'll see you next Tuesday.